In this video, we begin with the derivation of the rate law for an enzyme-catalyzed reaction according to the Michaelis and Menten mechanism. Alright, so Michaelis and Menten were the pioneers in the study of the kinetics of enzyme-catalyzed reactions. Right, so the idea is that you can have a reaction like this, which is simply a substrate to give product reaction catalyzed by an enzyme. And what Michaelis and Menten did first was to measure how the rate for the reaction depended on the concentration of substrate. Right, so that determines the rate law. And the type of measurements that they did, they just measured the initial rate, V0, as a function of the concentration of substrate. Right, and what they discovered is that the way that this rate dependence on the concentration of substrate looks like is something like this. At low concentration of substrate, you have a linear dependence on the rate, but then eventually that dependence saturates, and then you have that at high concentration of substrate, there's actually no dependence of the rate on the concentration of substrate. Right, so it turns out that this is the equation of a rectangular parabola, which you can write simply as V0 is equal to a constant times the concentration of substrate over a constant plus the concentration of substrate. Okay? We can justify why that expression bears out this function. Right? We can say what happens at high concentrations of substrate, first at low concentrations of substrate. Okay, so we take a concentration of substrate that is very low. Then what will happen is that in the denominator you can neglect the concentration of substrate with respect to the constant V, and then that yields a rate that is going to be equal to A over V times the concentration of S. Alright, so yes, at low concentration of V you see that there is a linear dependence of the rate on the substrate, and that corresponds to this linear increase of the rate with the concentration of substrate. Conversely, if we actually have a high concentration of substrate, what is going to happen is that you can neglect the concentration of the constant V with respect to the concentration of substrate, and then the rate law turns into A concentration of substrate over concentration of substrate, which is simply equal to A. Right? So the rate no longer depends on the concentration of substrate, and again you see that the rate does not increase or decrease; it stays constant after some value of the concentration of substrate that is very high. Okay, so what we actually know is that the rate law has this shape, and then the question is, well, what is the mechanism that gives you that rate law? Okay, in the prior chapter we have seen how the mechanism of the reaction is responsible for the rate law. Okay, so in this case we're going to try to work backwards, right? We already have the rate law. This is something that we can measure. The question is, how do we then figure out what the mechanism is? Right, so Michaelis and Menten then did this work, and the mechanism that they proposed, that they put forward to justify that rate law, is something like this. You have an enzyme-substrate interaction first, okay, which looks like this, and it's a reversible one. Okay, so the enzyme-substrate complex can revert back to reagents. The rate constants for the forward process is K sub A, and for the reverse process is K sub A prime. That's the first step in the mechanism. The second step in the mechanism is enzyme plus substrate reacting to generate enzyme plus products. Okay, and this is characterized by a rate constant K sub B. Now, this is a little of a simplification from the mechanism originally put forward. In reality, what happens is that in this process you generate an enzyme product complex, and that enzyme product complex separates into enzyme plus product. But it turns out that this final step is very rarely rate limiting. So we can actually neglect it altogether, okay, and then assume that you simply get products, okay, directly from the reaction of ES. Again, it's a simplification, but it's one that it works well. Of course, if you add up these two steps up, then you actually get that reaction mechanism. Alright, so in the next, or what we can actually do right now is try to figure out then what the rate law for this mechanism would be. Okay, so it's actually much easier to think about the rate of product formation than the rate of reagent disappearance, and we actually can write the rate law for product formation simply as this. The rate, which is going to be the initial rate, to be able to compare it to the experiments, this is simply going to be the rate of this step, because that's the only step that generates products. Okay, so this is going to be equal to K sub B concentration of the ES intermediate. Alright, so this was our initial rate law, and of course this does not look anything like that. Okay, what we're actually going to learn then is how to work through the reaction mechanism so that we can replace this ES intermediate as a function of substrate and see if we can actually reproduce those experiments. Okay, so in the next couple of videos we're going to see strategies to be able to work with this mechanism so that we can actually, again, replace this concentration of the intermediate as a function of substrate and see if we can capture that measured rate law.